Our goal in the next part of 0005 is to establish a theory of dimension for vector spaces. Informally, the dimension of a vector space is just how many free parameters it takes, so how many parameters from the field over which you have your vector space it takes to specify an element of that vector space. Like, for example, if you have an element of R2 like this, it takes two independent parameters, which are real numbers, to specify one of those. So informally, R squared has dimension 2 for that reason. But making a formal theory of dimension, which is supposed to measure how large a vector space is, and making this apply to absolutely every vector space, is somewhat tricky, and it requires some quite complicated definitions. The first of those being linear independence, which we're going to discuss now. Before I talk about linear independence, I have to define a linear combination of a collection of vectors. So here's the definition. If you have a vector space capital V, and if you have a sequence of elements, V1, V2 up to Vn in V, for any n you like, then a linear combination of V1 up to Vn is simply an element of V which you can get by adding up a scalar multiple of V1 and a scalar multiple of V2 and so on, up to a scalar multiple of Vn. So here, these L's are supposed to be scalars, so elements of the field over which V is a vector space. Let's look at a quick example of this. So if we take our vector space V to be R squared, so this is a vector space over the real numbers, and if we take V1, vector V1 to be 1, 1, and vector V2 to be 1, 2, and vector V3 to be minus 1, minus 1, then one linear combination of V1, V2, and V3 would be V1 minus 2 V2 plus 3 V3. That's an element of our vector space R2, and in fact is equal to, in the top I get 1 minus 2 minus 3, and in the next position I get 1 minus 4 minus 3, like this. So this vector, which happens to be equal to minus 4 minus 6, is a linear combination of my vectors V1, V2, and V3. Now we're ready to define linear independence and linear dependence. So an important part of the definition which I'm about to read out to you is that linear independence is a property of a sequence of elements of a vector space, not a set of elements, a sequence of elements. This is important. Sequences have orders, so they have an order, right? A sequence of elements comes in a particular fixed order, and you're allowed to have repeated elements in a sequence of vectors. So this is different to a set of elements. It's important to remember that linear independence is a property of sequences and not sets of vectors. So the definition is, first of all, that a sequence V1, V2 up to Vn of elements of a vector space V is called linearly independent if the only scalars you can find, such that L1 times V1 plus L2 times V2 up to Ln times Vn is equal to the 0 vector. So here, of course, that 0 should have a subscript V, it's the 0 vector in V, are the scalars which are all 0. So in other words, the only linear combination of V1 up to Vn which is equal to the 0 vector is the linear combination where all the scalars are taken to be 0. Next point is that a sequence which is not linearly independent is called linearly dependent. So if you're linearly dependent, just means the opposite of linearly independent. Let's look quickly at an example to try and get this concept understood. So we will take as our vector space V to be our simplest non-trivial example, R squared, that's a vector space over the real numbers, and we will take V1 to be the vector 1, 0, and v2 to be the vector 0, 1. These vectors are linearly independent. And I will often write Li as short for linearly independent. So checking linear independence, which we're about to do for these two vectors, is easy. All you have to do is to try and solve the equation that says a number times v1 plus a number times v2 is equal to the 0 vector. Once you solve that equation, if the only solution is that the two numbers must be 0, then they're linearly independent. So let's do this. To see this, suppose that we have two numbers, a and b, so two real numbers because we're working with a vector space where it's a vector space over the real numbers. So suppose they satisfy a times v1 plus b times v2 is equal to the 0 vector, which in our vector space is this. Well then, what can we say? We know the definition of v1 and v2, so let's just write this out. What do I have? I have a times 1, 0 plus b times 0, 1, and that's equal to the 0 vector. So, just simplifying that left-hand side a little bit, what you've got is the vector AB on the left is equal to 0, 0. Okay, but if the vector AB equals the vector 0, 0, then actually A equals 0 and B equals 0. Alright, we've shown that the only linear combination of v1 and v2 that's equal to the 0 vector is the linear combination when A equals 0 and B equals 0. That means that our two vectors v1 and v2 are linearly independent. Now let's try an example of some vectors which are not linearly independent, so which are linearly dependent. We're going to stick with the same vector space. V is r squared, but this time we're going to have three vectors. v1 will be 1, 0, v2 will be 0, 1, and v3 will be 1, 1. Now I claim that those vectors are linearly dependent, which again we'll often write LD for short. Well, again, to show that these things are linearly dependent is straightforward. All you've got to do is write down a linear combination of v1, v2 and v3 which is equal to the 0 vector, but in which not all the coefficients, the scalars in that linear combination, are equal to 0. And it's fairly simple for us to do that, because if I take v1 plus v2, that's going to be the vector 1, 1, minus v3, well, that will be 0, 0. So there is a linear combination of v1 and v2 and v3, which is equal to the 0 vector, and where the coefficients in that linear combination, the scalars, are not all 0, right? The scalars are 1, 1 and minus 1, so actually none of them were 0. So these things are linearly dependent. So there is a piece of terminology which we need to use, which is a linear dependence relation. A linear dependence relation is what you use to show that some vectors are not linearly independent. So it's a linear combination of those vectors which is equal to the 0 vector, but in which not all the coefficients were 0. So I'm going to write that up here. A linear dependence relation for elements v1, v2 up to vn in a vector space V is a linear combination of the v's equal to 0 so let's say L1 V1 plus L2 V2 up to Ln Vn, which is equal to the 0 vector in V, but in which not all of those scalars L1 up to Ln are 0. So it's okay if some of the LIs are equal to 0, but not all of them can be equal to 0. So a linear dependence relation is what you need to show that a collection of vectors is not linearly independent. In other words, is linearly dependent. And this thing we looked at the bottom here is an example of a linear dependence relation for the three vectors v1, v2 and v3 in R squared. Linear dependence is a really important concept for us. We will use it all the time, so we're going to do a few more examples just so that we are going to get more confident with using the definition of linear independence and linear dependence. So let's take another example, this time in C squared. So we will let 1, 1, so let's call this V1. V2 will be 1 minus 1. Be elements of the complex vector space C squared. Okay, are they linearly independent or are they linearly dependent? You should think about this. Pause the video and try and decide for yourself whether those things are linearly independent or linearly dependent. Okay, I hope you did it. Well, they are linearly independent in C squared. Remember, Li is short for linearly independent. To prove this, you just have to try and write down a linear combination of V1 and V2 which is equal to the 0 vector and show that the only such linear combination is the one where both of the scalars were equal to 0. So let's do it. For suppose that we have two numbers, complex numbers, because we're working in a vector space over the complex numbers. Such that A times V1 plus B times V2 is equal to the 0 vector in our vector space, which is this. Well, if you just work out the vector A times V1 plus B times V2, what you will get is A plus B in the first place and A minus B in the second place. And that is equal to the 0 vector 0, 0. So A plus B equals 0 and A minus B equals 0 at the same time. Right, well, what you have there is a system of linear equations. You know how to solve systems of linear equations. And in general, very much of the time when you're trying to determine whether some vectors are linearly independent or linearly dependent, what you'll be doing is solving systems of linear equations. So it's lucky for you that we spent all that time in the first or in the previous part of this module learning about how to solve systems of linear equations. So for this particular system, it's very easy to do it. You can just do it by hand. If you add one equation to the other, then you'll get 2a equals 0, so a equals 0. And if you subtract the two equations, you'll get that b equals 0. So this implies a equals b equals 0. These two simultaneous equations can be solved to get a equals b equals 0. So what we've shown there is that the only linear combination of v1 and v2 equal to the 0 vector is the linear combination where both of the scalars, a and b here, were 0. So v1 and v2 are linearly independent. Now, of course, if you had more complicated vectors, maybe bigger column vectors, so that your linear independence check required you to solve a bigger family of simultaneous linear equations, then maybe you'd need to do that systematically. For example, by taking the system of linear equations, forming the appropriate augmented matrix, putting it into row-reduced echelon form. That's a standard way which you learned for solving complicated systems of linear equations. But here, because our system of linear equations was so simple, so small, we could just do that by hand and see that the only solution was a equals b equals 0. Okay, let's try another example. So I'm going to do what looks like the same example, but isn't. So what is that other example? So now let v1 be 1, 1 and v2 be equal to 1 minus 1. But this time we're going to think of those as elements of F2, the field with 2 elements squared. So we're thinking of these as column vectors as height 2, whose elements come from the field with 2 elements. So what about those? Are those linearly independent or linearly independent? What do you think? Again, pause the video and think about it. All right, well, I hope you did. And the answer is that these things are linearly dependent as elements of F2 squared. Linearly dependent. Right, the reason for that is in the field with 2 elements, minus 1 is equal to 1, because minus 1 and 1 differ by a multiple of 2. In fact, they differ by 2. And you'll remember the definition of the field with p elements, Fp, was that the elements looked like integers, except we regarded 2 integers as being equal if and only if they differed by a multiple of the prime p. Here we're talking about F2, the field with 2 elements, so minus 1 is equal to 1 because minus 1 differs from 1 by a multiple of 2. So in fact, in our vector space, v1 equals v2. And that means they're linearly independent. Sorry, that means they're linearly dependent, because v1 minus v2, well, you can just work this out. What do you get? You get 1 minus 1 in the top place. In the second place, you get 1 minus minus 1, which is 2. And of course, in the field with 2 elements, that's equal to 0, 0. So what you have here is a linear combination of the vectors v1 and v2 in which not all of the scalars were 0. Again, in fact, none of the scalars were equal to 0, but that linear combination was equal to the 0 vector. So these things are linearly dependent. Now actually, let's look at a more general example. So in fact, in any vector space, if you've got 2 equal vectors, then they're going to be linearly dependent. So in any vector space, V, if v1 equals v2, then the sequence v1, comma v2 is linearly dependent for exactly the same reason. v1 is equal to v2, so v1 minus v2 is a linear combination of v1 and v2 with not all scalars equal to 0, but which equaled the 0 vector in our vector space V. Let's write this a little more neatly like that. Okay, in any vector space, if you've got 2 equal vectors, v1 and v2, then the sequence v1, v2 is linearly dependent. Okay, more examples. I really want to get this linear combination, linear independence concept clear, so I'm going to do some more examples. The next one is a exotic vector space where the elements are not just vectors or matrices. So here is vector space F, which we met before, and this is the real vector space consisting of all functions from the real numbers, so with domain the real numbers and codomain the real numbers. So this, as you'll remember, is a real vector space. And it contains two elements, cosine and sine. Okay, there's a cosine function which takes real numbers as inputs and gives a real number output, and there is a sine function which takes real number inputs and gives real number outputs. In other words, has domain and codomain the real numbers. So those things are elements of f. And again, we're going to ask the question, are they linearly independent? And again, you should think about it. Pause the video, decide for yourself, are they linearly independent? Okay, I'm sure you did. I know you did. And I know you got the right answer, which is yes, they're linearly independent. So if A times cosine plus B times sine is equal to the zero element in our vector space, well, let's think what that means. This is an equality of two functions. On the right, the zero element in our vector space, as we saw a couple of lectures ago, is the constant function which is always 0. And on the left you've got a function which sends a number x to a times cosine x plus b times sine x. So if this equality of functions is true, then a times cosine of x plus b times sine of x is equal to 0 for all x. All x. So in particular, it's true for x equals 0. Well, what happens when x equals 0? Cosine 0 is equal to 1. Sine 0 is equal to 0. So a plus 0 equals 0. And therefore a is 0. On the other hand, it's also true for x equal to pi over 2. Cosine pi over 2, if I remember correctly, is equal to 0. I had to think about that for a moment. So actually we know a equals 0 anyway, so the cosine term is going to give us nothing. And sine pi over 2 is equal to 1. So b times sine pi over 2 is equal to b. Again, that's equal to 0. So alright, well, what have we done? We took a linear combination of these elements cosine and sine of our vector space, which was equal to the 0 element of our vector space, and we've proved that the coefficients in that linear combination, the a and the b, actually had to be equal to 0. So we've proved that these vectors, these elements of this vector space, are linearly independent. Alright, one final example then before I stop, and I'm going to leave this one for you to decide. We are going to work in the vector space R cubed, and here are three vectors in R cubed, 1, 2 and 3. V2 is going to be 4, 5 and 6, and V3 is going to be equal to 7, 8, 9, you guessed it. So these are going to be thought of as elements of R cubed. So are they linearly independent? This is the problem I'm going to leave you with. So what I will do is to just try and explain how you can solve this problem. Well, what you're doing is you're looking for numbers A, B, and C, not all 0. So real numbers A, B, and C, not all 0, such that A times V1 plus B times V2 plus C times V3 is the 0 vector in R cubed. So the way you can do this is simply you can work out what this vector is, and you can set that equal to 0. And what you'll find is you have 3 simultaneous linear equations in the unknown quantities A and B and C. You can solve those linear equations and you can find the solutions for A, B, and C. If you find that the only solution is A equals B equals C equals 0, then they're linearly independent. If there is a solution in which one of, or at least one of A, B, and C is not 0, then they're linearly dependent. So I'm going to leave you with that problem.